Okay, we want to thank everybody for joining us today. This is the research results presentation for the study Long-Term Validation of an Accelerated Polishing Test Procedure for HMA Pavements. The study was conducted by the University of Akron under the direction of Dr. Robert Liang. He is here to give a presentation on the project. The presentation is going to be recorded, and a link will be available on the research website shortly after this. In a couple of days, you can go back and view it later or send the link to some colleagues who weren't able to attend today. The PowerPoint will also be available on the website, and the final report will be available as well in the upcoming couple of weeks. If you have any questions during the webinar, please email those to research@dot.state.oh.us. The email address is at the bottom of your screen. Other than that, Dr. Liang, it's all yours.
Okay, thank you very much, Vicki, for your introduction, and good morning. Well, I should say good afternoon here in Ohio for those of you who come to the conference room. And I know there are some folks out on the West Coast. And I would say good morning to you. Thank you for joining us today for this webinar. And I would, I guess, take this opportunity to present the research result that was a long time to come, because this project was almost 3 or 4 years in working. And prior to this project, there was a previous project that was for the development of a research-grade polish device for testing the hot mix asphalt surfaces. So today I will focus on the this current research results. So to begin with, I would just show you the topic or outline that will walk you through in today's talk. I will give you a very brief background in terms of the motivation and objective of this study. Then I will show you accelerated polishing machine. There are 2 versions of this. One is developed previously. We call it a research-grade polish machine. And you can see there's a lot of validation, trial and error type of work done in that phase of the work. And with that, then we engaged local machine shop to help transform that into a more commercial grade or production grade polisher that can be used by laboratories for the testing purpose. I would then talk about the procedures used for polishing and measuring the friction behavior of laboratory compacted HMA specimens. And I will then go on to describe the field work that involved the monitoring and measurement of some friction values using different devices. Finally, I will talk about some of the models that we developed that will help transform the laboratory result into forecasting of the performance of those HMAs in the real pavement service condition. I will show you at the end applications of those models, and then hopefully it can be very clear at the end that the whole test machine, polisher, together with the interpretation method of the test result will be very easy, and hopefully it's painless for Ohio DOT to look into the possibilities of using it maybe down the road. And I will finish up with conclusions, recommendations for implementations, and also some suggestions for some future work. As you know, the work never stopped. So it's not we want to continue to have a research, but I think it's prudent to have more data systematically down the road to continue to validate and improve our predictive models. So why are we motivated to try to develop a laboratory scale accelerated polishing machine to study the friction behavior of hot mix asphalt surfaces? Well, I guess you can read this slide. You can see that the accident, 25% of all crashes and 40% fatal crashes involved a pavement that is wet. But also a study done by some other folks indicated that statistically there is a relationship between the skid resistance as measured by skid number, SN, and the occurrence of the accident on wet pavement. So we can see that there is connection that skid number or the friction value of the surfaces of the pavement can be one of important factors contributing to accidents, particularly those fatal accidents. So therefore, it is very important for DOTs to look at the ways to monitor the friction of in-service pavement surfaces, or to develop a laboratory procedure so that we can determine the performance of the mixes during the mix design. So the idea of this project is to see if we could develop appropriate simple procedure to accomplish the goal of being able to tell whether the asphalt mixes would perform well from the friction point of view. As I mentioned, that almost all the agencies throughout the state are more or less developing some kind of skid number requirements for the need to either to have investigation on that particular section of the pavement or to do some remediations to improve the skid number or frictions. So here I compiled some of the requirements that we can gather from the literature. And one of the particular points I want to mention here is the one in red. That is Ohio DOT's most recent report done in 2008, which was geared towards the looking at the statistically any correlations between the skid number on the pavement surface and wet accident events at a particular section. And from that report, a number was presented to indicate that there is a need to basically resurface or to improve the skid resistance on a particular section if the recorded or measured skid number is about 32. If you use the rib tile for the measurement purposes. So that's kind of the number, although it's tentative, maybe it's not very conclusive, but this is the one number we can find that indicated that 32 seems to be a relatively low level of importance. And you compare to other states, you can see that 32 is relatively low compared to many other states. So you can see that criterion is not necessarily very high standard criteria. Okay, so getting into the objectives of the study, I can boil it down into two things. One is that we want to develop accelerated polishing machine and accompanied testing procedure so that it can be used for initial screening purpose of the mix, particularly related to the selection of aggregate. As you know, that aggregate constitute perhaps more than 95% of volume or weight of the asphalt concrete, and the friction value and the textures of the aggregate itself plays an important role in controlling the frictions of the HMA. So, however, the mix design itself could also affect it, because if you have a more binder or if you have different grades of binders at different temperatures. The polishing behavior may also be different, even though you use the same aggregate source. So the idea here is that rather than using the existing testing methods, such as using the British wheel polisher, we would like to kind of polish the HMA. Okay, so the point here is that there are other devices available to really polish the hot mix asphalt surfaces, but those test procedures are somewhat cumbersome, requires a special setup and special sample size for testing. And as you will see, our objective here is to make it to be part of the mix design procedure so that the HMA samples that you prepared from a gyratory compactor can be used as well for the friction and polishing test. So that's the first objective. The second objective, of course, is then to see whether we can take more advantage of the data we obtained from the laboratory test. Since we do the test on the polishing test on the HMA for almost 6 to 8 hours, there is a time-dependent friction degradation that you can get from the laboratory test. So the idea here is to see whether we can extrapolate this time-dependent degradation curve for us to forecast what is the friction loss behavior during the actual pavement service conditions. So that's the second objective. So in this talk, I will show you the machine that we developed and the procedure that we suggested to Ohio DOT for consideration, as well as the interpretation procedure or the predictive model that we can use to predict in-service friction loss behavior. Okay, the requirement for the accelerated polishing machine is listed here in this slide. You can see we want to use the small size specimens, particularly it is already produced when we do the mix design, such as using the gyratory compaction method. The test itself should be relatively short, so we have to accelerate the polishing action in the lab. It has to be relatively simple, meaning that you do not want to involve too many measurements, too many types of measurements. So we have to make a decision in terms of whether we want to measure, for example, the images of the surface of the pavement samples, or we want to do more detailed texture measurement, so on and so forth. So as you can see at the end, we want this procedure that's not necessarily involving many different measurements. Rather, it should be straightforward. And then the other requirement certainly is that the test has to be efficient, meaning that you don't want to have a person stand in front of the test machine and watching it all the time. It has to be less labor intensive. Finally, of course, the main idea is that we would like to be able to polish the samples in an accelerated manner, but it would then produce the friction, residual friction number that you might get from the real tile welding and tilting of the pavement surfaces. So those are the points that we need to follow when we develop the laboratory scale polishing machine. So I'm showing you the earlier version. We call it research grade accelerated polishing machine. So since it's a research purpose, so it's a rather huge machine, and it is really add-on type of devices that so that we can do many different type of trial and try to narrow down the operating parameters and to narrow down some of the important controlling parameters when we operate in the machine. So I show you some close-up photos. You can see those are the kind of makeshift controlling device where we can look at the power generated. We can measure the speed, and we can look at the the load, vertical load applied to the specimens, so on and so forth. And also there's a source of a water supply to cool down the temperature between the polishing disc and asphalt samples. So as you can see, this is kind of as you can expect it for a research type of equipment. Then the details of the polishing is shown here, and this forms the basis for the current generation of commercial grade machines. So what you can see here is actually this research grade machine can accommodate two types of specimens. One is a very small 6-inch diameter gyratory compacted specimen, as you can see on the left. Well, this is a slab specimen. So this is almost like a 2 feet by 2 feet by 3 or 4 inches of roller compacted slab. So then we use the rubber, a very specially made, a custom-made rubber, to rotate with constant force, with constant speed on top of the asphalt concrete surfaces, so that with this direct and flat contact between the rubber disc and the asphalt surfaces, you can see that the surface being smoothened or polished. So the friction will become less and less with increasing of the polishing time. So this particular picture is showing you that we can test very large size specimens that's compacted by the roller compactor. And the reason we choose this dimension is that this sample size can be used for dynamic friction tester and the CTMs. So dynamic friction tester has a required diameter or the radius of the machine when they try to measure the friction. And when we do the CTMs, it's the same dimension as the DFT, dynamic friction tester. That's why on one set of the tests we will have DFT and CTM measurement for both friction and textures. And this is the picture of samples mounted for the small-sized samples, right? So you can see it's a 6-inch diameter, either 4-inch or 6-inch high cylinder specimens that can be subjected to the polishing. Again, principal polishing is the same as for the 2 feet by 2 feet slab specimens. Basically, we're using a custom-made rubber disc to rotate on top of the asphalt surfaces with constant force and constant rotational speed. And this is actually just a schematic diagram showing the cross-section of the device. So the whole idea is that in this research phase of the work, we want to compare the friction measurement for two different sizes of the specimens, and are compacted with two different construction methods. One is gyratory compacted, the other one is roller compacted. So in the previous report, actually, we indicated that the compaction method really did not affect the friction behavior in terms of what's the final friction number you will get, so on and so forth. So this is the very important finding from the previous phase of work that helped us to narrow down some of the operating parameters. For example, we kind of fixed our rotational speed at 30 RPM. And the vertical force for 6-inch diameter specimen, for that cross-section area, we require 290 pounds. And there's a need for the water to get into the interface between the rubber disc and the asphalt sample surfaces. So the amount of water flow is also fixed over here. It's about 100 milliliters per minute. And the total test duration, we set it for 8 hours. So presumably a lab person coming in the morning can push the button, start the testing, and by the time 8 hours, that's about in the afternoon, the time he can go home. So he doesn't have to run the test overnight. And the test result shows that after 6 to 8 hours, we can reach what we call the final friction number or residual friction number. So that time is kind of optimum for the day-to-day testing purposes. So the laboratory work involves some kind of measurement. As I mentioned, we have two types of specimens. One is 6-inch gyratory compacted. The other one is 2 feet by 2 feet roller compacted samples. Those are done in the previous phase of the work, but those are important for us to be able to say, okay, we can just limit ourselves to the 6-inch gyratory compacted samples without worrying about 2 feet by 2 feet specimen, because in order to produce that big specimen, it really is a very intensive effort. No laboratory on daily basis would like to produce that kind of specimens, right? So, but any of the procedures listed here, when we have a sample prepared, we first have to measure the friction value using a British pendulum tester. Then we put the specimen into the machine and subject it to 1 hour polishing. So after 1 hour polishing, we will then stop the machine and then take the specimen out. We remeasure the friction using the British pendulum tester. So you can record the friction number, or BPM, we call it, British pendulum number, as a function of time of polishing duration until it's at 8 hours. And then at that point in time, the whole test is complete. And of course, I mentioned to you some of the measurement devices. So this is for the big 2 feet by 2 feet slab. And on the left, lower left, you can see is the dynamic friction tester. That's an ASTM standard machine where you can measure the friction value for the ring. You can see that on the big specimen there. That's why we need that big specimen, because the dimension of this dynamic friction tester is such that you need that circumference of the ring to measure. You can see there are 3 rubber pads at the bottom. That's where it measures the friction with different speed. So friction actually is the function of the speed as well. And on the lower right side, you can see it is what we call the CT meter, or circular texture meter. Actually, it's also a ASTM standard test procedure with this standard test machine, where you can measure the texture of the surface on that ring you see over there. So those are very standard ASTM procedure for measuring friction as well as the texture for the big specimen. And this is the one of the test results. You can see that on the upper half, you can see it is the friction measured by dynamic friction tester versus the polishing time. And of course, we get to 8 hours. So, so in fact, in this particular case, we carry it out longer. And you can see the friction is decreasing with polishing time until it gets to maybe 600 or 500, 600 minutes. And then you can see most of the cases that the friction value is more or less constant, at which time actually the friction will not decrease anymore. This particular friction is called the residual friction, or the final friction value. At the same time, you can look at the lower half of the curve. It indicates the texture, mean peak MPD, which is actually the texture measured by the CT meter. And there's a procedure in the ASTM that would allow you to compute this. And you can see that the texture also becomes smoother as the polish time gets longer. For the 6-inch gyratory compacted samples, the only way we can measure friction due to the small size of the specimen is to use the British pendulum tester. Of course, everybody knows that the different friction measurement device, because they are measuring friction at different speed, they will give you different friction values. That's the complexity of this friction bitterness. And of course, the friction also depends on the texture. So that we would, at the same time, measure the texture by using the sand patch method. So both of these, again, are the adopted ASTM standard. Okay, so the most important part of the work is that we selected 8 different mixed designs that was used for 8 different pavement projects. And we kind of have friction behavior of the aggregates for those mixes. So we use the standard British British wheel polisher on the aggregates. So we kind of understand what kind of a polishing behavior the aggregate would be using this ASTM standard British polishing device, which is different from what I'll show you here. So we kind of labeled those mixes as L1 to L3, which indicates a low friction susceptibility, low friction loss susceptibility. That means the aggregate tends to maintain very high friction values. And we have also so-called medium ones, M1 to M4, which we consider to be kind of most of the aggregates, limestones, will fall into that category. And finally, H1 is one of the suspected, maybe it's because of different minerals in the limestones that make it more susceptible to polishing and also produce smaller friction values at the final stage of the polishing. So important point here you can see here is that if you look at the 3 groups, and we also look at the now the initial BPM, those are the mixed specimens subjected to the procedure I just described to you with our polishing machine. So this is the mix now, not the aggregate itself. You can see we have an initial BPM, we have a final BPM, we have to decrease delta BPM, and you can see that by and large for L category, which is high friction resistance mixes, average decrease in BPM value is about 20. For M1 category, you can see that the final BPM is in the 54, 55 range. And the average drop from the initial value to the final value of the BPM is about 30. The one that we thought it would be probably more susceptible in terms of the friction performance is labeled as H1, which has a lower final BPM value, which is in the 40s range, and then the percent decrease is more from the initial BPM value to the final BPM value. So those are the mixes that we try to follow in our field monitoring program to see how the friction value in terms of SN will change over time for those pavements with those mixes. Well, unfortunately, some of the pavement right after we initiated our research got repaved. So some of those would not have historical data from the field. Okay. And this is the same mixes with the change in textures as measured by sand patch method. You can see the similar trend because the texture MTD decreases. That means that the surface is smoother, and there's less, rough surface involved. And that means less friction value as well. So you can see it's kind of matching in terms of the decreases in the friction number and decreases in the surface roughness, or the MTD, so to speak. So again, you can see the categories of L, M, and H, and the amount of decreases in MTD kind of in conformance what we anticipate for these three categories. Now I plot this time-dependent friction degradation curve for three categories. And here is the medium one. You can see the final friction number is around 55 based on the BPM test result. Here we have two other categories. On the left, we have L category. You can see the final friction BPM value is around 60, so that's pretty high value. And you can see they don't diminish with additional polishing. So they stay on that level. So they are pretty good performer. But the one on the right is, has the BPM value dropped down to about 45. Okay, so this is the one that may eventually will cause problem in terms of frictions and skid numbers. Now I want to show you that we also look at the images of the surface just to give you some idea, because I don't have the specimen with me. You can see the left column of these images showing the real picture, the photos of the surfaces of the samples. On the top one is before polishing action, so 0 minutes. And in the middle, it's about 240 minutes of polishing. And finally, at the end, at the bottom, it's 8 hours of polishing. So you can't really touch this, but you can see there are two things you can see. One is that there's more welding down the binders, so the aggregate surface being exposed due to the polishing action that we perform on the samples in the lab. And you can see with the graph showing here, there's, with time of polishing, there's more percentage of the aggregate area being exposed on the surface. The column of the images on the right, the vertical column of the images on the right, actually is the digitized images of the real photo on the left that will allow us to measure the percentage of the area of the aggregates being exposed without a binder on the top of the aggregate. But if you touch this specimen, you can see that really at 8 hours of polishing, it's very smooth. It's almost, but the picture itself wouldn't tell you the smoothness or the touch of the friction. So that's the laboratory test result for 8 mixed design with different categories of aggregate, L1 or M1 or H1. And with those 8 mixes, there are 8 pavement sections that built with those mixes design. And we kind of try to gather the friction data on those pavements over the years. So we typically do it once a year, typically in the spring, late spring, early summer, to measure the friction values and the textures on those pavement surfaces. And we did that for 4 to 5 years, depending on when the pavement is online. Some of them are new pavements, some of them are existing pavements. Here is the location of the pavement surfaces. Most of them are District 11, District 3, and some of them are District 2. So some of those sections, as I mentioned, that we lost the data right after the selection of those mixes because of the district has that plan already in work, and because the friction value is kind of the pavement condition is such that requires the resurfacing. In the monitoring or in the field testing, basically we have identified the location where we want to measure the frictions and the textures. And typically we take a pavement, we mark every 0.5 miles to have 1 point of measurement. And most of those measurements are on the wheel pass, on the left wheel pass. Okay, you will see a picture of that. And for this point, we have a mile marker and also the location marked. So every year we go back, we will measure the exact spot when we do our measurement. And we'll measure several different things. Particularly, we're measuring DFT. That's the friction using the dynamic friction tester. We also asked Ohio DOT to provide the skip number measurement, and it's a coordination between us and ODOT. We tell them, okay, this month we have done these sections, and hopefully ODOT can send, the testing device, LWST, to measure the skip number for that particular section in that particular time window. Of course, we try the best. Sometimes it may not be exactly the same month. So there's some variation contributing to the scattering of the data for sure. But that's the best we can do, because even that skip number measurement is not measuring precisely the same spot as we're measuring using the DFT. So we have to really take the average of whole pavement section to take that number as kind of an indicator of the friction value for that particular mixed design using those measurement points. So you can see here is some of the photos showing the work being carried out in the field. And this is probably just two-way. So we do both directions. And this is the DFT being used to measure the texture. And this is the dynamic friction tester. It does require water, so we have to carry a water tank with us when we do the dynamic friction testing. And we also measure the BPT. And it was later. Initially, in the first couple of years, we didn't have this kind of measurement. Okay, so I'll show you some of the trend lines. And you have to look at this data with some kind of grain of salt, because it's real data that happened in the long stretch of the pavement for each mix, right? So anyway, we'll go in. So what you see here is that each year, typically, you can see there are 2 points. Right? Because we have two directions. The eastbound or westbound. So in 2 directions, you're not going to get the same value. Right? So we just plotted to show that it's the 2 directions. But each point represents the average of the entire pavement section. So for example, the previous slide, you can see how many data points we have. Let me go back here. We have for each section. For example, Harrison Route 22. We have 12 measurement points. So each point is separated by half a mile. So 12 points we're looking at, this is 2 directions. So there's 6 points in each direction. So it's about 3 miles long of the pavement section that we are measuring with those 6 points. So you can see that there will be a lot of scattering from one point to the other point. So that has to be recognized, because the field work is not like in the lab. You have a clean specimen, you got very nice curve. Okay, so here is the trend. We fit the trend line to show that indeed there was some diminishing trend. Well, if I plot that line, you can then kind of be misguided. Well, anyway, if I don't plot that line, you may well say, oh, there will be no trend. But so anyway, it's a visual guide to help you to see that there are some actions going on, and some of the sections are not necessarily the best plot. You can see, like for example, M4, that it's quite scattered. But for others, maybe it's not that bad. So anyway, so those are the real field data. And this is actually the data provided by Ohio DOT for those sections. We label it as L1, M1, so on and so forth. All right, so you can see we lost H1 right away. We don't have that. There are other things, for example, dynamic friction testing. we can see that M4 is kind of standing out in terms of scattering on the both directions. But others, you can see that DFT has more consistent data compared to, for example, SN, skid numbers, by the LWST. So again, it's the different devices. LWST is running at a highway speed, 40 miles per hour, and it's running with, Vicky, you have anything? Oh, okay, I thought you tried to stop me or something. But anyway, that's what it is, okay? It's the field measurement. Then we have DFT 64. It's just a different speed. One is 20 kilometers per hour. This one is 64 kilometers per hour, because DFT is capable of giving you the friction values at different speed. And this is an MPD as measured by the CT meter, okay? And we have some BPM measurements as well. Now, International Friction Index, IFI, is the one that most people are trying to use to indicate the friction values, because we have different devices for measuring friction. As I already indicated here, we have skid number measured by the LWST. We have a DFT, friction measure device. We have BPN. So we already talked about 3 different devices. The friction value measured by each device will be definitely different, because they are different devices. And also we understand the speed is important and the texture is important. So this International Friction Index is an attempt to harmonize all different testing devices and to take into account of the speed. So it is an ASTM standard, and so we use different devices to get this F60, which is actually a unified or homogenized friction value, take into account of the speed and measuring device differences. So here is, this is not a measure, this is calculated based on the data we reported earlier, right? So this is the variation of F60. Now for us to build our prediction model, we basically look at F60 as well as SN64, because those are 2 friction values that ODA may be using. I know ODA right now is using skid number for monitoring the friction on the pavement surfaces. So now I have introduced you the laboratory test result for different mixed designs of field monitoring data for those pavements built with those mixes. So the next step is to introduce you the product that may be implemented or adopted by state highways if they consider this particular polishing mechanism acceptable. So we have engaged through the ODA funding a local machine shop based on the idea I just described to you, those operating parameters, and build a very, very robust, supposedly relatively cheap polishing device. We call it the polisher. And so in the report, we just call it the polisher. So here I'm going to show you some of the photographs. I was joking with all the folks earlier. I didn't bring the device here as a demo. It's just too heavy, because everything is by the, for example, the vertical force, we talk about 290 pounds. Actually, it's by dead weight. It's a weight. It's not a pneumatic device, because we want this to be robust and durable. It can be used for a long time. So there's no microelectronic chips embedded here. Everything is kind of mechanical. Everything is controlled by knobs and so on and so forth. So here is the front view of the polisher. You can see we have a control panel built on the left. emergency stop. Everything is according to the industry safety standard. And on the right-hand side, you can see there's a access door for you to get in the equipment, test equipment itself, and to put a specimen onto the machine. And this is the what we call the chamber. You can see that it has several, apparatus built in. And you can read this as well as I can. So we have a sample tray. We have a particle track. That is, when you polish it, there's a lot of residues of the asphalt aggregates and rubbers that have been polished into powders, and they're going to drop onto the tray, collecting it. We have a clamp that easily clamp the specimen, holding it tight. We have a water supply with the shut-off valve, and the water supply can be regulated with this indicator here. And also, because we have water constantly flowing into the specimen, and we have water drain to drain the water out. So everything is built so that it's never going to require a lot of labor force, brute force, to put a specimen into the machine. And this is the critical part of the component. This is called a polishing disc, and this is the rubber mounted that can be basically mounted on the top, holding device. The rubber has two groups, so that it helps those residues or polishing residues would not accumulate it on the polishing surface, because if it happens, then the polishing surface would not be flat. And sometimes it creates the rocking actions or pitching actions. So with the introduction of these two groups, it helps smooth out the surface without the effect of the polishing residues from the asphalt or from the rubber. And this rubber is dispensable, because after one test, this rubber is going to kind of consumed a lot, so it cannot be reused. And this is the water flow meter. As you can see, it's a very simple control by adjustment knob. And here we have a control panel, and you can see that nothing fancy. We have on and off switch. We have emergency stop. There is two modes. One we call the manual mode, which is really for you to check everything is ready. Auto mode is that when everything is ready, then you can just switch to the auto mode. Then it will run automatically for 1 hour and will stop by itself. You don't have to time it. The machine can time itself. Every 1 hour it will stop, and you can come in and take the specimen out and measure the friction using the British pendulum tester. And after you have done that, you put it back on, switch hit the on button again. It will continue on for another hour, will automatically stop, and then allow you to take the specimen out and to continue your operation. So it's fairly user-friendly, very, very, requirement on the operating personnel is very, very minimal. Here is the samples. On the left, it's a 6-inch diameter by 4-inch height gyratory compacted specimen. We do have a spacer there because the height, we want to accommodate two different heights. On the right, you can see it's a 6-inch height specimen. And now here is the, when we bring down the rotating rubber disc, you can check the alignment. So this is like manual operating mode. You can even check the water flow, so on and so forth, before you hit the auto mode. Then it will start running by itself. And we did some comparisons with this new, what we call it, production grade polisher with the previous research grade polishing machine. Since the operating parameters are the same. The rubber disc material is the same. So we will assume that the result of these two test machines should be the same. So we run some comparisons, and this is one set of comparisons. You can see on the top we have a research-grade polishing machine, and then the bottom we have a new commercial-grade polishing machine. We put these two curves, actually 4 curves together. You can see that there is not much of a differences in terms of friction polishing behavior that you can get from the new machine that you can get from the old machine. Right? So it's kind of one of those quality assurance of the new machine, making sure it's operating, producing the same result as we have done using the research machine. So at this point in time, I'm going to switch my gear to talk about the model that we developed for predicting the friction behavior from the laboratory test procedure that I just described to you. There are 2 models. One is the model to predict the skid resistance, SN, skid number. There's another model for you to predict the International Friction Index, F60. All right. So the basis of the model is actually looking at the friction degradation curve that we get from the, we're supposed to have 8, but we look at 5, 6 friction curves. And we try to find a function that can reflect the degradation of the friction with time. So the function that we find out is this one on a model function, which we think is very powerful because it allows us to change 2 scales. I will get to that later on. So basically, it's a very simple mathematical function that fits very well with the degradation curve that we observe in the lab. So the explanation of these 2 important coefficients, one is T0, the other one is power M. Right? So what does it, why does it matter? So basically, with the same equation, with the same BPN 0, if I hold my M value to be constant, I just change my T0. This is actually something I will describe to you later on. It's an index reflecting the time scale. So I'm trying to transform a laboratory time scale into field time scale. All right? So this T0 is the important function to allow me to change the scale. And you can see on the left-hand side of this curve, you can see by changing T0, you basically change the time for reaching that final friction values. Right? So if T0 is small, then that means that you will get, I'm trying to see the curve. T0 is high, that means your time to get residual friction value is short. If T0 is small, then it takes longer time to get to the final friction value. So just remember T0 actually is a time scale to see how much time it takes to go from initial friction value to the final friction value. What is M? Well, M is a scale, what we call scale index. That's how much friction loss you're going to get. Well, if your initial friction value is 68, as indicated on the right-hand side of the curve, if you fix your T0 but change your M, you can see that with different M value, you will get different decrement or different loss value of your BPN or skid number, right? So basically, by knowing what is T0 and M in your model, then you can predict how BPN is going to change with real-time T, right? So this is the mathematical model telling us that the friction is going to decrease like this power phone, right? Actually, it's exponential decay. But these two controlling parameters, T0 and M, would reflect, one, the material intrinsic properties, because M is actually how much friction decrease you're going to get. What's the difference between the final friction value, initial friction value? For the for the material that has a lot of friction change, the itself indicates the aggregate may not be good or mixed design may not be good. So that's reflected by M. How fast the polishing would happen, actually it's a function of not just the material itself, it's a function of the traffic. What's the traffic count on the pavement? What kind of traffic you have. So there are external factors affecting T0 and M, right? So we want to reflect those external factors, how that affect your T0 and M. Once we can identify those, then we will be able to predict based on what we observe on the laboratory, right? So that's kind of logic behind it. We use this very simple, yet I think it's very powerful. We don't want to build a very complicated mathematical model because then it's kind of difficult to implement. So with this simple mathematical equation, all we have to know is how to determine T0 and M. So while we look at a lot of other models being built around the nation, and particularly the one that's ongoing in Texas, because it's much more complicated in Texas. They have to use many different test devices to predict the degradation curves for aggregates, so on and so forth. But we kind of draw some knowledge base from their report, and we look at our data that we have. So we decided that we're going to look at 4 predictors. So over here we can see we have average daily traffic, ADT, that reflecting the traffic count on the pavement surface. We have this polishing value. Polishing value actually is, I mentioned to you, is the normalized friction decrease. Right? So material L1 has 20%. Material M1 may be 30%. And material H1 may be 35%. So that's kind of material intrinsic friction loss characteristics. So that's one of the predictors. This has to come from our laboratory test. Right? I have to determine what is the BPN at time 0 and BPN at time 8 hours. Since I'm doing a test, I should get these 2 values. With these 2 values, I can find polishing value. So that's the one of the predictor reflecting the material properties. So I have a traffic as an external factor. I have a friction performance from the accelerated laboratory test as one of the predictor. In addition to that, I have another 2 parameters, which is reflecting the aggregate gradation curve. So I use kappa and lambda. So I promise there's only 2 Greek here in my presentation. So kappa and lambda, I will show you what it means in terms of gradation curve in the next photograph, next slide. And what we try to see is then I can relate those 4 predictors to 2 responses, T0 and M. That's the important coefficient in my model. So I'm saying these 2 coefficients or regression constant will be controlled by the material friction characteristics, by the aggregate gradations, and by the traffic count. Okay. So what's the meaning of lambda and kappa? So I just show this graph to show you how that control your gradation curve. And I apologize, my students, usually this axis should be large particle size on the left and small particle size on the right, but he switched it, but it's okay. So typically it would go this way, but it's going this way. It's the same thing. So on the vertical axis, you have a percentage passing. On the horizontal axis is the seed size. All right, so you can see by changing K or kappa, I'm sorry, that's Greek. You can see it kind of dictates how uniform or non-uniform your gradation curve is. You can see this one is non-uniform because predominantly one size of particle. If you have this blue one, so it's a kappa equal to 1, it's more well-graded. Right? So it's kind of representing how well-graded, how uniform graded your gradation curve is. The other one is the lambda, which actually is showing whether you have predominantly large size particle or small size particle. So you take 40% passing, you can see the blue one, the particle size is about 0.05 inch. But if you go to the purple one, actually it's large particles, right? So it tells you the size of the gradations. In fact, this lambda and kappa were used by Texas DOT when they look at their models as well. So this is nothing new. We just took from them. And actually, it's a function representation that's proposed in Texas DOT. So I won't go into the details because this is a linear regression, but it's a multivariate linear regression. What we're trying to do is we want to take the traffic data that we have. We want to take the polishing value we have for the mix from our lab test. We want to look at a gradation curve, lambda and kappa, for our aggregate used in the mix. We take those for each payment section. So if I have, in this case, I have 5 or 6 payment sections, or 5 or 6 payment materials. For each payment material, I will have different ADT, PV, kappa, and lambda. So I'm trying to figure out what is this regression coefficient, which then will help you to determine your T0 and M. Right? So the exercise here is taking our database that we have and to figure out if we want to estimate what is T0, what is M, we can just plug into these 2 equations as long as we can find this regression coefficient, alphas and betas. So now it turns out this is the final model that we have. So if you want to predict the skid number over time, then you need to figure out what is T0, and T0 is computed by this equation. And of course, you need to have an aggregate gradation curve to figure out what is lambda and kappa. You need to use our polisher to determine what is this PV. You have to know what is the anticipated average daily traffic for the payment. And then you can find your T0. Similarly, you can find your M. So the T0 and M, once it's determined for the particular mix design, for the particular payment traffic condition, then if you know what is SN0 initial skid number, then you can predict what's the skid number going to change with time. So that's the prediction model. So the key here is that we do have to use our laboratory polisher machine to determine PV, because this is material intrinsic friction characteristics. And this reflects the aggregate used gradations. And then ADT is more payment section specific in terms of traffic. Now, the key here is, of course, in the laboratory test, we cannot measure SN0. So for your prediction purpose, we have to convert BPA into SN. And this particular empirical equation was developed by Ohio DOT sponsored project for I think, University of Toledo. And it was based on substantial amount of database at that time. And we did some independent check. Of course, it would not always match because it's a statistical correlations. Okay, so one could debate about this because I think some of the DOTs do not like to convert SN to BPM or vice versa, but some of the DOTs think it's doable. But Ohio, we take this particular equation, we run our particular data. I think it's kind of within the range we're looking at. So that's, but if you can, after you build your new payment, you can go back and measure SN0, then you don't have to do this. then this becomes a very powerful prediction equations, I think. And I show you some of the prediction results because I said there are 4 sections we use to see how our model can predict, and you can be the judge how good it is. Of course, the data itself is kind of scattering, so we kind of look at the trend. Notice that the SN0 at time 0, some of the pavement we do not have that, so we convert the BPN0 to SN0 for these comparisons. Okay. So R squared typically is between 80% to about 95%. So we consider it's okay, knowing that the data is going to have a lot of noise. The friction behavior in the field has so many other factors. I think California study shows that, for example, if you have a dry period time, and then you go in to measure friction, which will be tremendously different if you have heavy rainfall, and after that you wait for maybe 1 week and you go measure. So it is highly variable depending on the temperature, the time you're measuring friction, the precipitations, and so on and so forth. So it is not necessarily going to be point-by-point correlations. But I think the trend is very good. And also, I think it's important is that we can capture the residual. The curve is not going to go all the way down because it's not realistic. So we can see that up to a certain point in time, the friction is not going to decrease that much for that particular material. It's kind of a residual steady-state values. The same story that we can describe for the predictive model for F60. So I'm not going to go into much of detail, but in doing F60, we introduced 2 additional predictors. One is the texture value. So it's reflected by this value. This is the MTD measured by the sand patch, because this is a laboratory measurement. We only have 6-inch surface area, so we cannot use the CT meter. So we only can measure the mean texture depth, MTD, using the sand patch method. So you have to measure the texture before polishing and the end of 8-hour polishing. So this is the indication of how much change in the surface roughness. All right. So that's one additional predictor if we want to get into International Friction Index. The other predictor is called the T-stable. Actually, it's a time for reaching the residual steady-state friction value in the lab. So you have to take a look at the degradation curve and figure out maybe it's at 8 hours, you got to steady state, or 6 hours. So that's the time when you reach the steady state friction behavior during the polishing. So with the same procedure, we look at all the 5 or 6 pavement sections that we have data on, and you can see that we use the same model here. So we can predict International Friction Index friction value, F60, as a function of T, depending on the regression constant. One is the time index, T0, which again is now it's a function of 6 predictors rather than 4. All right, so we have traffic, we have a friction value loss, we have a time to reach stable, we have a texture loss, then we have kappa and lambda for the gradation curve. So just adding 2 more predictors in our predicted equation, since this F60 involves the measurement of the texture. So we do have to have this included. And this is 1, 2, 3, 4, 5, 6, all 6 sections that we predict the F60 using the DFT and the CTM to calculate F60. You can see the predictions are matched relatively well with the measurement. Some are well, some are not necessarily very well. So you can see that Huron 162 is kind of not, because the trend itself is not following that power loss kind of curve. Okay, so I probably should speed up a little bit. This is the procedure that we wrote into a supplemental note so that Ohio DOT can take a look to see whether it makes sense or not. So the first thing is to describe the laboratory test procedure for determining final friction number. So it's a very simple procedure. You put your gyratory compacted samples into the polisher machine. You run 8 hours. Then you measure what is the final BPN value. We call it BPN final. So it's a very straightforward 8-hour polishing. We know all the samples that we run will reach the final polishing friction value after 8 hours. Some of them reach that before 8 hours, but we just make it consistent. Run 8 hours, you will be able to get your final value. So this is the example. Let's say for this example, we run 3 specimen identical samples. And of course, when we measure the BPN, we need to repeat, right? 1, 2, 3, 4 trials to measure the BPN. You can see sample number 1, BPN value 76, 76, 75, 75. So average of the first sample is 75.5 for initial value. And then I have 3 samples, then I can take the final BPNs over here. So we have initial value 76.75 and final value of 54.92. So that's how we run 8 hours, then we get the numbers like this. So in terms of screening, we mentioned that SN equal to 32 seems to be a very low threshold. It's not really very high standard. And it's indicated in that report suggesting to Ohio DOT, really when you get I think they said when you get to 45, you start investigating. When you get to 32, really have to do something. So for us, I think recommending 32 as a cutoff really is very, very fair. It's not very, very high standard at all. And so what we do is you put into the BPN and final, the number into this empirical equation, you will get SN final. So most of the aggregates mixed design is going to pass this requirement. The only one that would not pass is the one we call H1. So M's and L's will all have a higher SN number than 32. So it's not going to create a lot of problems to aggregate source or any mixed design at all. But I think it's a step forward in terms of being able to have some test procedure and have some minimum requirements so that we don't really use those mixed design or problematic aggregates. Now the other is the procedure for determining the friction degradation curve. And so this is an example. So you have to measure every hour. So previously we only look at the final BPN number. Here, in order to build an entire curve, then every hour you have to stop and take the measurement. And so the example here just show you the possible time history of the friction changes. And this is what you get of the degradation curve. So you will use, in our method, you need to use BPN at time 0 and BPN at 8 to calculate that PV. Now, we are going to provide a simple spreadsheet or Excel type of a program or instruction so that if you have an aggregate gradation curve, which is your input, by going through a very simple commands through your Excel, you can get lambda and kappa. It's all built in, so you don't need a special program at all. So this is the process. You know, you click File, Options, Add-ins, Manage, and then go and choose those options, and then click OK. It will run. So I think we will write a very, very simple instruction. We can even provide the particular script if ODOT needs that, so that when you have a gradation curve, you can figure out what is the kappa and lambda very easily, just by using the spreadsheet or Excel. We already gone through this, so I'm not going to. This is just an example of how use this data to calculate a T0 and M, and then we can then plug in the equation. So the equation we have here is Sn at any time t is computed by this equation, and those two constant is based on the calculation we have based on the data I just showed you. So you can see if I carry out the calculations, I put t equal to 5 years, 10 years, 15 years, 20 years, and 25 years, you can see how the skip number is going to degrade with time for this particular material with this particular traffic count. And you can see it will probably get to residual value. It will not change that much after that. Okay, so this is indication of a very good mix design, very good aggregate source, and you know, theoretically the friction is not going to be a problem for your pavement surface, because after 25 years you still have a skid number about 43 for this particular mix design and aggregate source. So the conclusions, we have a new commercial grade accelerated polish machine called the Polisher, and that's developed and validated, and we're ready to deliver to all the lab this week, I guess. It's been packed, ready to go. We have comparison test between the research grade machine and Polisher, confirms the operation of the Polisher machine. I think the Polisher can be used to determine the polishing and friction behavior of HMA surfaces. We have developed a supplemental note in which a step-by-step procedure was presented for obtaining the residual or terminal friction number of a given HMA mix. This can be used to judge whether the mix design will be performing well from the friction and polishing point of view. We can also use the friction degradation curve from the lab test to forecast what is the performance going to be for that particular mix in the actual pavement surfaces. Implementations, of course, this is just the suggestions. We suggest that if this polisher could be looked upon and see whether it's a simple enough device for possible adoption. And of course, the supplemental notes for the screening purpose, as well as the prediction models. All these are suggestions for Ohio DOT to consider. Finally, I think it's very critical that somehow the material office and pavement office set up a systematic way of a database in the future, so that all the pavement surfaces, when they have a skip numbers, they can monitor it, and they can take that mix design, use the device they are going to have in the lab, run the test to get a degradation curve. And with that, you can then see how good the prediction model is going to work for many, many other pavement sections. I think it's critical to continue to get the data and to validate and check on this particular approach that we mentioned here. It's very simple. Hopefully it can do the job, but it's kind of showing good promises and good comparisons for all the sections that we monitored. So I think that's the last page I have. Appreciate your time. I run really long, but we still have 10 minutes for questions. Thank you.
At this time, we're going to open up the floor to questions. If you're watching on the webinar and you have a question, please email it to research@dot.state.oh.us, and we will forward that on to Dr. Liang. If there's anyone here in the room who has any questions, just raise your hand.
Hi, Bill.
Yes, Robert, I had a couple of questions. Is there a standard temperature at which you do the polishing?
Room temperature.
Just room temperature?
Yes.
Okay. The other question is, were the materials that you used in the lab to compare with the field that got from the same sources as were in the field?
Yes, it's the exact source of aggregate, exact binder grade, exact mix design.
Okay.
We replicate those samples.
Because I remember way back when we did some skid testing that there seemed to be quite a difference in skid-resistant histories depending on the type of sand you use, whether it was manufactured sand or natural sand.
Okay.
And that might affect some of your equations and so forth. I don't know. But
yeah, the field performance is somewhat scattering. It's not necessarily follow that particular line, that curve, but I think it's kind of telling us the degradations are going to go from the initial value to the final value within 20 years, 25 years. And so the two controlling points, the initial value and the final value. How that changes, of course, the field performance is going to go up and down, not follow the same curve.
In fact, we restricted the use of manufactured sand back in because it tended to provide slippier pavements, so it was always natural sand was required. I don't know if that's still the case or not, but that's the way it was.
Well, I think we have some sand and gravel aggregates in our. I don't recall that's. I think it's. I don't know. It's natural sand or it's a manufactured sand. I think it's natural sand, right? I recall. It's so long time ago. I don't remember.
Well, the effect of the fines has ultimately. You mentioned the shape factor, gradation curves. Ultimately, that's what's critical because fines may or may not be an important factor depending on that shape factor.
Yeah, but he's talking about the differences between the manufactured sand and natural sand,
right? Which
we didn't really look at that carefully. But the presence of fines or sand, amount of that, that's reflected in a gradation curve, that lambda and kappa parameters.
Okay, we have a question from the internet. How you measure the percentage of aggregate exposure after polishing?
Oh, it's just we transform the real photo into digitized photo or binary file. And then we have a software that can really look at a grade level. Because the exposed surface, the grade level is different from the binder itself. So we use the grade level and then be able to define the boundaries of the aggregates and the binder. And from that, we will be able to calculate the percentage of the area of the aggregates. And there's a software already available for us to do all that task.
Trying to think of how to, trying to think about how to phrase this question. Basically, your prediction of the loss or final skid number is based on the polishing value that you get from your conditioning of the sample, plus a factor based on the gradation of the materials.
Yes.
So my question is what is the sensitivity of the numbers to the two factors? Is gradation as important as the polishing value, or is one more important than the other? Or?
Very good question. I don't know, because when we build a model, we try many different models. None of them works as well as this one. So I think those factors are more important factors in being able to kind of get some match. As I said, whether this one is more important than the other one, I cannot tell you. We may be able to go back to scratch our head to see whether we can do some sensitivity analysis or importance analysis based on the equation we have and the coefficient we have here. But that's a very good question. I didn't look into that in terms of which one is important on the
And
other.
I don't want to beat the dead horse, but where I was trying to get with it is, is the gradation going to color the results a lot, depending on what the gradation of the mix is?
I know what you're getting at. It's the same question I was talking about, percent of fines and all that, and but how sensitive this curve is to the gradation lambda and kappa. Realistically, we did not look into it. We could look into it. I did just show you how lambda and kappa affect your gradation curve. But in terms of once you have this lambda and kappa, how sensitive is your degradation curve to this? But I think the important thing here is that that's only affecting how fast your degradation curve is going to be. It's not going to dictate what's your final number, because the final number comes from your lab test result. So the final number, the BPNF final, that's kind of fixed. The initial value is kind of fixed. It's just how this degrade with time and traffic and your gradation curve that kind of change that shape. And I think by my conversation with Dave, I may be wrong, is that this model may not necessarily be the one adopted at this point in time, but the minimum number may be the one that kind of is like a low threshold. We're looking at a final friction number. But the model itself probably needs a little bit more cases. So, but we put it there just so that when people can try it out to see what it looks like. Yeah. But I get your point. Yeah. And so the sensitivity of the gradation curve, or I think even Texas DOT, they do the Michael DeBall to get aggregate. And they have some kind of numbers taken from there. And also they have to use many other empirical equations. It's fairly complicated. And they haven't gotten to the point actually compare their predictive models with the performance data yet, I think. Yeah, Fred.
Thank you, Dr. Liang. In the one slide you had, and it goes back to Bill's question there with regard to the gradation of the material.
Yeah.
And I believe this lambda factor has to do with the size of the aggregate. Is that correct? Well,
yeah, let me.
Perhaps it's slide number 48.
Okay.
Perhaps I'm just misinterpreting that, but my question goes to whether or not you observed any difference that you could make some sort of, I guess, remark as to whether the size of the coarseness of the mixture as to its the type of result, how it might affect the result. For instance, fine textured mixes versus coarser textured mixes. They may still be well-graded mixes, but one having a finer aggregate top size versus one having a coarse aggregate top size. How or what effect might that have had?
Yeah, I think that's this lambda is the one that kind of look at the particle size and your top size and how much large particle size you have. It's kind of reflecting that. But as far as what is the behavior predicted by our model by changing this, we can go back and run some cases to see how the model is sensitive to the variations of gradations in terms of the uniformity, also in terms of top size aggregates. Well, I think
But at this time, you don't have that.
I don't have
that
off my
knowledge.
head because I didn't look into that. I just trying to match my predictions with the performance data we have. I really didn't look at some of the issues, material issues that may be of interest.
Dr. Liang, I would say with regard to Cliff's question there that we will have the software that will make that kind of work rather simple to do.
That's right.
So
Yeah,
it can
you
be done at a later
put
date.
some. Yeah, I think you just put some real aggregate gradations put in there and run with the same predictions. Just everything kept constant, but just changing the gradation characteristic. You can see how sensitive that is. Yeah, it's not. Yeah, not very difficult. I just didn't look into that from that angle because it's not kind of scope at that time.
We have another internet question for you. They're using a 3-wheel polisher by NCAT quite a bit. Are you aware of any correlations between that device and your own?
I'm not aware of the NCAT is from Alabama and National Center for Asphalt. I forgot. I think in the literature review, is it a tripod? They have a 3-wheel running on it? Sorry,
With regard to that device, there's a recent update on that device, and their work with field correlations,
as I said. Yeah.
their work with field correlations is quite limited at this point in time. And there is no direct correlation between what we did here in Ohio and NCAT.
Right, we did not really compare that. And I'm aware of this, but essentially you need to have 3 wheels running.
And also, just regarding the dimensions of your sample, any preference between the DFT measurements and the BPN measurement?
Okay. Of course, DFT measurement is I think it's probably better because it can measure the friction at different speed. So that's the pros. But the cons is that you do need a very large specimen or sample size. So from the practice point of view, no laboratory is going to be willing on daily basis or on routine basis to produce such a big sample size. It has to use the roller compactor to produce it. So the BPN actually only measure the friction at low speed. But I think as long as we can establish the correlations with sufficient confidence, I think that BPN number can still be used as an indicator of the friction.
Yeah, I've got 2 questions. One is with the rubber disc.
Yes.
Are there any specifications or tests that we would do on that to ensure that the properties of the disc aren't changing or they're within a particular criteria? That's the first question.
Yes, there is a mixed requirement for the rubber. It's spelled out in a report. Yeah.
Okay.
It's very important to
Right.
have the same formulation.
Okay, second question would be, if we cut a 6-inch core, it wouldn't be quite 6 inches. Would it make sense to compare the 6-inch sample with the gyratory compactor with an actual sample taken from the field? Could you test a 6-inch core that was,
A bit smaller than I said.
a little bit smaller? Yeah.
I think the device should be, because the clamp is not fixed in terms of, it has to be exactly 6 inch. So the clamp can hold the sample, yeah.
Okay, well, if you don't have any more questions at this time, we'd like to thank everyone for participating. If you do come up with questions later that you would like to have Dr. Liang address, you can feel free to email those to research@dot.state.oh.us, and we will forward them on to him. In a few weeks from today, the recording of this presentation, along with a PDF of the PowerPoints and the final report, will be available on the research website. You can download all that from there. Thank you all for participating, and thank you, Dr. Liang, for the study.
Okay, thank you very much.